Today, we're going to pull back the curtain on one of the deepest architectural secrets in large-scale AI. We're talking about modularization and functional cohesion. And trust me, it's the key to understanding how these massive systems don't just collapse under their own weight.
Which brings us right to the central question, the billion-dollar question, really. You see these giant AI models getting bigger and bigger. So how do they actually do it? How do they scale without imploding? I mean, just take a look at this. This is a map of a high-density AI architecture. It's an absolute maze of interconnected parts. And as these systems get bigger, this complexity, well, it becomes the #1 enemy of performance.
So yeah, we're not just talking about a minor headache here. This is a full-blown scaling crisis in system design. The challenge is figuring out how to manage this insane explosion of internal communication and just keep the whole thing running fast.
Now, what's our first very human instinct when we're faced with a huge mess? We tidy up, right? We start putting things into boxes, files into folders. In software, the most basic version of this is creating what we call namespaces. They're just logical labels to group related code. It looks clean, it feels organized, but as we're about to find out, just looking tidy is nowhere near enough.
To really solve this scaling problem, we have to think way beyond these simple digital filing cabinets. We need to start thinking about modules not as neat little containers, but as actual units of performance.
And this leads us to a huge, fundamental shift in thinking. It's captured perfectly in this one sentence from the HDA architectural principles. Modules in HDA are not merely namespaces. They are not there just to make the code look pretty for a developer. Nope. They serve a much deeper, much more physical purpose.
So what is that purpose? Well, this slide lays it out perfectly. It's like a battle between two completely different philosophies. On one side, you've got your old-school namespaces. They're just logical groupings. The goal? To make things look tidy. But on the other side, you have these things called cohesive modules. And look at how they're defined. Execution locality units. Their goal isn't about looking tidy. Their goal is to run fast. The whole focus shifts from human convenience to raw machine performance.
And this brings us to the hero of our story today, the principle of functional cohesion. This is the secret sauce. It's the design rule that actually makes high-performance scaling possible.
So, what is functional cohesion? At its heart, it's a simple, powerful idea. Components that talk to each other a lot, I mean constantly, should be physically grouped together in the same module. This isn't about what makes sense logically, it's about the physics of making the data travel the shortest possible distance. And here's the cool part, you can actually measure this. It's called the cohesion ratio. The best way to think about it is as a teamwork score for a module. It basically asks, how much of the work and communication is happening inside this team versus how much time are they wasting talking to other teams?
And the goal? It's crystal clear. You want that cohesion ratio to get as close to 1 as you possibly can. A score of 1 would mean a perfectly self-sufficient team that never has to talk to anyone else. You're maximizing that fast internal chatter and killing the slow, expensive cross-country calls to other modules.
Okay, so a teamwork score sounds great in theory. But how on earth do you measure that in a real-time system with millions of moving parts?
Well, you need a very special kind of tool. For this architecture, it's something called the Call Frequency Matrix, or CFM. You can imagine it as a giant, detailed social network map for every single component in the entire system. It tracks who's talking to whom and exactly how often. And this matrix gives you some incredible insights. But one of the most important metrics you get from it is something called call entropy. You can think of it as a measurement of chaos. It tells you how disorganized and unfocused a module's communications are. Is it talking to just a few close friends, or is it just yelling randomly into the void?
So, when you see that call entropy number start to creep up, huge red flags should be going off. It's a classic symptom of an architectural smell known as utility drift. This is what happens when a module that started with one clear purpose slowly becomes a junk drawer, just a random collection of unrelated functions. Its teamwork score plummets, and so does its performance. So it's pretty clear that enforcing high cohesion gives you massive gains in efficiency and performance. It makes everything faster. But like with any really powerful technique, there's a flip side. There's a hidden danger. But first, let's just appreciate the payoff, because it is huge. High cohesion directly translates to better hardware performance. We're talking higher cache reuse, because the data and instructions are physically close together on the chip.
You cut down on the overhead of jumping all over the code base, and, crucially, you keep most of the messy feedback loops contained inside a single module. This is all about raw metal-to-the-pedal speed.
But here is the twist. What happens when you create these perfectly optimized, super efficient little teams? You've made them so good at talking to each other, so tightly knit, that you've accidentally created a brand new, and honestly, a much more dangerous kind of risk for the system as a whole.
And that leaves us with a critical and kind of scary cliffhanger question. How do you prevent these hyper-efficient, tightly knit modules from creating a runaway feedback loop that could spiral out of control and destabilize the entire system? We'll dig into that very problem in our next explainer.